Hello and welcome to Data Structures for Graphics lecture, which is a part of the course on computer graphics at KAUST. Today we will be talking about various data structures which are often used in graphics. We will start with the most frequent representation, which are the triangle meshes, and we'll be describing what are the suitable data structures for representing it or for processing it, for finding necessary information we might be interested in. The second part of the lecture will be dedicated to scene graphs or spatial data structures, which will be organizing our scene in order to perform certain search within the scene faster for example, purpose of accelerating ray tracing. And the last part of the lecture will be dedicated to tiled multidimensional arrays. So let's start with the part on triangles. Our most common representation in computer graphics is a triangle mesh. A triangle is an element which is concatenated with other triangles, forming a larger structure which is approximating by these small areas, planar areas, and curved surface of a particular object. By certain tricks, like for example, by smooth shading approaches, these planar surfaces will become invisible to the most of the viewers and will be sufficient for approximating otherwise a complex shape to describe. Now we need to somehow store these triangles, and some objects can consist of several thousands, maybe even millions of triangles, and therefore their efficient storage will be necessary in order to store or transport this data from memory to memory. So these triangles consist of vertices, and these triangle meshes are in fact connected triangles through these vertices and edges which are spanned between these vertices. So in fact, we can on one hand store these triangle meshes as individual triangles, but that would be a rather inefficient representation, especially if you think of that on the vertices we will be storing not only their positions, but also additional information, such as texture coordinates, shading information, maybe animation, or their irradiances, meaning the material properties. Therefore, we need to think of what data structures can we use so that we do not need to store each vertex for each triangle separately, that we perhaps can represent these vertices in a form where we do not need to have duplicate entries for vertices. In order this to work, we need to often have several constraints on what structure our mesh can represent. So there are various algorithms which will work perfectly well, but their assumption is somehow restricted to just few of the possible triangle meshed objects. Such as, for example, if a mesh is considered as a 2D manifold, then it will be a closed watertight object which has no holes, and there is always on a certain neighborhood on this surface, it can be always approximated by a planar representation. We will see that on the next slide. Furthermore, this is rather restricted representation because that would allow us only to represent closed objects. But sometimes we have open objects, such as, for example, a terrain where we have a boundary at some point, and that will be that will be an sort of relaxing this constraint to the category of manifold with boundary, for which most of the mesh processing algorithms will still work either straight away or with slight modifications. So without going into details of defining mathematically correct what the meaning of the manifold or two manifold, we will constrain our definition of manifolds to two conditions for the triangle meshes. In these two conditions, a manifold is a triangle mesh in which every edge is shared by exactly two triangles. So if you think about that, this condition will not hold for an object which would have a hole in itself, or because on that hole the edges will have just one triangle, or on the boundary. So this condition will not be fulfilled for manifolds with boundary, but that is understood. At the same time, um, every vertex, the second condition for the manifold to, uh, to be a valid manifold, is that every vertex has a single complete loop of triangles around it, meaning that there is nothing like, let me draw it for you perhaps, like a set of triangles like this and another triangle like this. So this vertex here will not have a single complete loop of triangles because there is a missing space here, and therefore this mesh will not be a manifold, even if otherwise all the other condition will be fulfilled. Now, we can also spot easily whether a mesh is shared, edges shared by two triangles in this following way. If we, for example, have some effect like this shark fin, sometimes it might happen that our triangle representation will have three triangles to share a edge, and that will mean that such an representation, such a point on the edge, as we see here, will not be possible to approximate by a flat, planar, small patch, as it will be possible here. So this is a condition which is fulfilled to be a manifold on the edge, while this one on the left is not. For vertices, if we look at this triangle on the right, pyramid on the right here, we can see that this apex is formed, or it is participating on various triangles which are forming this pyramid, but around it we can always make a complete loop of triangles around it. And also what we can see here is that it can be, even if it's very sharp, it can be made planar as an approximation of this area. So it is still fulfilling the condition of a manifold. This is not the case on the left image, because here there are two pyramids connected, and the neighborhood around the vertex is not a single complete loop of triangles, but actually two loops. So this will not be a structure which would be a two-manifold. Another aspect which we need to consider in meshes which is important in order for many structures to work properly, is that our mesh should have their triangles to be oriented in a certain way consistently. So for example, if we have several triangles, we would like that all of them are with their normals pointing in towards the same direction, and not that one normal will be, I'm sorry, not that one normal will be pointing downward, so to say. Um, that would be incorrect. It would be inconsistent orientation of triangles. So for orienting the triangles, we define an order of our vertices which form this triangle. So if we look at the image on your right hand side, there we have two triangles connected together. We can call them CBA is one triangle, and the other triangle is ADC. And we see that they are oriented, these two triangles, so I will write them down. CBA is oriented in a counterclockwise manner, as this arrow indicates. And the same holds for the other triangle, which is ADC. This is also defined in a counterclockwise manner, as we can see. So, and as a consequence, we can see that in on the edge which they are sharing, one direction for one triangle is in one way, and the other triangle has the orientation in another way, to be able to satisfy the condition of both are defined as an order of counterclockwise ordered vertices. We can see an example on this image here where this is not the case, and the edge is here called is having both triangles oriented the edge in the same direction. And we also can see that the second triangle, ACD, will be ordered in a clockwise order, its vertices, and that will mean that its normal will be oriented in the other direction than for the triangle BAC or CBA, if you like. So we need to make sure that we generate meshes that are consistent in orientation. So how can we represent the mesh through its triangles? One way, which will be the most straightforward, but at the same time not very efficient way, will be to represent each triangle, triangle 0 to 1 and 2, by just listing their vertices in the data structure. So that would mean that we have for our triangle 0 the values of the point vertex A stored, then B and C in this example, which is fine. But for the triangle 1, we will again have a B for the second time, D and C for the second time, and then for the second triangle, or third if you like, we have again A and again D, and again B. So these three triangles are in storing duplicate copies of those vertices, which will lead into inefficient storage or transmission of such data from one place to another. What we can do instead, we can create a so-called indexed mesh storage, where we first have a data structure which just lists as an array our vertices. In this array, we will have for each vertex, we will store its position, but also we will store its other non-spatial information such as texture coordinates, material properties, etc. Then we have a second, so this one is, so this is the array of vertices, and here we store the positions at least, but also the other information as I mentioned. And then we have another array of triangles in which we list our triangles and we only list which vertices does the triangle consist of. So in the triangle 0, we will have information that it consists of vertex 0, 1, and 2. So it will be the coordinates of the point A, B, and C. And for the triangle 1, we will have similar information stored, namely, again, indices of into the array of vertices to the positions of on which the vertices of this triangle are to be found. So 1, 3, 2 will be 1 is B, 3 is D, and 2 is C. So that will be the triangle 1. B, D, C. So this is the one. The previous one will be 0, 1. 2 will be this one. And the number 2 will be 0, 3, 1. A, D, B. So this is the triangle 2. So we can see that with this, we are not storing the vertices 9 times, but only 4 times, and then 3 times a vector of the indices to the respective vertices. And we can see that such a representation can be easily, or structure can be easily represented this way, where we have an indexed mesh, we have an array of vertices, and then we have an array of triangles, where each entry will have three, it says a two-dimensional array here, and where 0 would mean the first vertex, 1 would mean the second vertex, and 2 will mean the third vertex, which are forming our triangle. So this representation will be actually quite efficient, and it will in fact reduce the storage requirements by approximately factor of 2. We can see on this slide how we, for example, can address the or get to the positions of individual vertices which are constituting a triangle. We simply take the triangle which we have in mind, the ith triangle, and look at the kth vertex, and this information will be the index into the array of vertices where these positions are to be found. Now, Let's have a look at this example of a triangle mesh where we have several triangles and they are organized in this index mesh. Like for example, we have here this triangle 0 and we can see that this triangle 0 is having a P0 as its zeroth point, P2 as its first point, and P1 as its second point. And it is nicely aligned or defined in a counterclockwise manner. If we look, for example, at the triangle T1, there the P0 is again the zeroth vertex in this indexing here. Then the P3 is the first vertex and the P2 is the second vertex. Again, counterclockwise. And we can see that this similarly, we can see how these vertices are organized to form these triangles. And all of these triangles, which we can see here, are organized in their vertices in a counterclockwise order, meaning that all these triangles will have the same orientation. Besides the index mesh representation, we can further optimize our representation of a triangle mesh by data structures which will have even smaller memory footprint, such as, for example, triangle strips and triangle fans. So let's have a look at the triangle fans first. A triangle fan is a structure of triangles which share the same vertex, and this vertex is then present in every triangle. And if we define that some vertex is a fan, then the triangle set is a fan, then a fan can be simply described by a sequence of its points for P5, and in this case this will be a fan with a clockwise order, as we can see, because it describes the following triangles. The first triangle will be P0, so I will just write the indices 0, 1, 2. The second triangle, we will forget the P0 we will not forget. The P0 will always remain, but we will forget the P1. And then the next one will be 0, 2, 3. And then we forget the P2 and we will have 0, 3, 4. Then we forget again the P3 and we will have 0, 4, 5. And we can see that we have described 4 triangles just by describing it, that the sequence is a fan and describing the 5 vertices. So this is quite an efficient representation of 4 triangles. Another representation could be the triangle strip. So unlike a fan, it's more like an array of triangles. And the principle is that we always forget the oldest vertex and alternately swap or do not swap the remaining 2 vertices. So in this case, we have our points, our strip P0, P1, P2, P3, P4, P5, P6, P7, and we are defining with this strip the following triangles: 0, 1, 2, based on these three. Then we forget the oldest one, which is P0, and the next two we will swap. So we will have P2, P1, and P3. P2, P1, P3. So 2, 1, 3. And then for the next one, we are not performing a swap, but we forget the P1, and then we will have 2, 3, 4. And then we forget the P2 and swap. Then we will have 4, 3, 5. And then we are forgetting the 3, and we are continuing without swapping. So 4, 5, 6, and then for the last one, we forget the 4, and then the last triangle will be defined as 6, 5, 7. So this way we have defined a triangle strip and triangle fan with just a sequence of indices of these vertices. We have implicitly defined how they are connected in this higher level sequence of triangles. While this might look like some unnecessary optimization, where the memory will be saved after only very long strips or fans, this is actually not the case. Already for having 3, 4, or 5 triangles organized in a fan will save us approximately half of the storage. And infinitely long triangle strip will save us 2/3 of the storage. So it will only require 1/3 of the storage as compared to the vertex representation in a separate array and with an index mesh. Now, these representations are great for storing or transmitting the meshes. However, they are not very useful for editing meshes when we need to access the mesh for certain processing. Often, in processing, we need to access a particular triangle and find its other triangles which are neighboring it, other 3 adjacent triangles. Or we have an edge and we would like to find which triangles does this edge contain. Or for a vertex, we would like to know which triangles contain it, or which edges contain this vertex. And this all is possible to find from our data structures as we define them so far. However, finding them will require certain computational complexity. So, and optimally, we would like to find them in a constant time, meaning that we will not need to iterate through the entire lists or arrays in order to find the necessary information. So let's have a look at data structures which are enabling to search quickly in meshes to find the necessary information. The first representation is the so-called triangle neighbor structure. Here, in this representation, we will have our triangles 0, 1, 2, 3 triangles will always contain an index to the neighboring triangles. So you can see that triangle 0 is having a neighboring triangle 1, triangle 6, and triangle 7. And triangle 1 is having as a neighbor triangle 10, triangle 2, and triangle 0. So we have a neighboring triangles stored here in our triangle representation. Furthermore, as before, we are storing the triangle indices into our vertex array, where in our vertices we will have, for example, the vertex 0, 2, 1, defining our that the P0 is the zeroth vertex for the triangle 0, P2 is the first one, and P1 is the second one. So this is as it was before, and additionally we will have one array of vertices which with index of one triangle which contains them. Just one triangle, not all of them, arbitrary one which contains this vertex. With this representation, we will be able to, for example, find very easily which other triangles certain triangle is adjacent to, that is directly stored in this data structure, but also, for example, which triangles a particular vertex consists of or is part of. So let's have a look how we can easily calculate that. Here we have a short code for that, where we have our vertex as the input, and we know from this triangle neighbor structure that in our vertex array we have an index to one triangle. So we store this one triangle index into this variable t, and then we will be searching. We are entering this loop here where we are searching for which index has a vertex which forms our triangle T, which is equal to our vertex V. So we will find basically the order of it. And once we find that this is, for example, if let's say our vertex V is the vertex P2, then let's say we will find, I think the vertex P2 is referenced in the triangle 3, is referencing the triangle 3. We can see it by this arrow here, and then we will find that this P2 is the zeroth vertex in forming this triangle. That means that then we will be proceeding to next triangle, which is the zeroth neighbor. So we have found this I of the zeroth position of this vertex, and it is at the same time the zeroth position of where we are having our next triangle which contains it. So we have found that T3 is one triangle which contains P2, and the next one will be T2. And then we are again entering this loop, we are now having the t is storing the t2, and we are searching at which position is our vertex v. And the vertex v is at the p2 is at the position 1, because p10, p2, p3 defines the vertex, the triangle t2, and therefore we are searching for the triangle which is neighboring. So T and B are 1 will be here, and that corresponds to the triangle 1. So always the side which is emanating from our vertex P2 is, or it's closest to it, that is the 1. So this will be the 0 triangle is the T3, and the first triangle is T1, and the second triangle will be T12. So we found out that our next triangle is T1 around this vertex P2. And again, then we are looking, okay, P2 is the second in the 0, 1, 2 order of the vertices for the T1, and therefore this will be also the second neighbor. So we will be identifying the triangle T0, etc. And we will, in a clockwise order, find all the neighbors until we find out that our triangle T, which we have associated with in this command, is our original VT, so a triangle associated with our vertex P2. So, and then we have found the entire loop. Obviously, back to our discussion on for which types of meshes this will work. This will work for the manifolds, such an approach very well, but for non-manifold structures, this will probably not work well. Maybe for manifolds with boundaries, this could work. However, certain modification to the algorithms will be necessary. The triangle neighbor structure is already well designed for finding the adjacent triangles to a particular triangle, or to triangles which contain a particular vertex and make a complete loop around this vertex. Of course, when we will be having such an algorithm, it's not the only purpose to find these triangles, but this whole finding is meant for a certain processing or editing of the mesh structure. So that code we have not been presented, but that will be part of some particular algorithm. We are now concentrating only on the searching of the structures within our triangle mesh. This triangle neighbor structure has one disadvantage, and that is that we always need to find which triangle is the next one which we would like to go towards. And that is because we don't know when we enter a certain triangle through which edge for the triangle did we enter it. Therefore, we first need to find it out before we can proceed. And that can be circumvented by another approach, just a slight modification of the triangle neighbor structure, so that instead of storing instead of trying to find the particular triangle where to proceed, we will actually be able to easily compute it. To change the triangle neighbor structure from finding to computing the next triangle around a particular vertex is rather minimal. we can calculate it thanks to the expanding this one neighborhood information where we previously were storing the information about the neighbor being the triangle. Now we are changing that to being an edge data structure. In that edge data structure, we are storing the neighboring triangle, but also we are storing an index of this edge which it has in the triangle T. So we will have in the edge data structure a pair of a triangle and the index of this edge within that particular triangle. In addition, as previously, we will have the data structure of a vertex where in addition to all the per vertex data, we will have the information about this edge data structure. So not an arbitrary triangle, but an arbitrary edge which is leaving the vertex. Now let's have a look at how we can compute the proceeding or when we want to find all the triangles around a particular vertex. So our input is the vertex V, and we will first find out what is its corresponding edge. That will store us the pair of a triangle and an index of the edge. So if we have a triangle, if we have a point P2 again here, then the edge which we are having from this fetch will be this one, and it corresponds to the triangle T3. Now we are entering the loop around the triangle, and first we are obtaining a new pair of triangle and edge by fetching the neighbor which this triangle T3 has around this edge, which will be the T2. So it will be T2, and the edge index will be again what it will be 0, 1, 2. So it will be again 0. So this index for the T2, I equals 0. Now here we will be increasing the I to 1 because this is where we want to exit. We want to, it is easily computable through which edge do we want to exit. It will be just an increment modulo 3. So, and you can see that easily this is the case. We are interested in the edge I plus 1, which will be from 0, it will be 1, which is this one. And therefore, if we have the I now 1, we can find out for in our next loop that the neighbor for the index 1 will be then T1. And we will change our pair to T1, and the edge through which we entered was 0, 1. So it's 1. So for T1, I equals 1. And then we simply increase the I again to 2, and this is this edge within the triangle 1. So, and for that again, we can compute what is the neighbor, and it will be the T0. And the T0 has the pair T0, and the index of the incoming edge is I equals to 0. And therefore we can again increase it. Here is the I equals to 1, and the neighbor through this edge will be T6. T6, and which is this? Which one is this edge? It's not drawn here, therefore we It's not indexed here, therefore we don't know, but we can surely understand already this algorithm, how this proceeds. Always incrementing the edge by 1 is enabling us, and modulo 3 is always enabling us to compute the next proceeding triangle instead of finding it out. Let's have a look at even more refined data structure, which has the edge completely as the central part of our triangle mesh structure. It is the so-called winged edge mesh structure. Winged edge means that the edge will have some kind of wings, so you can imagine it as somehow metaphorically as a kind of bird. Let's, for example, have a look at our edge A to illustratively make a case about it. So for the edge A, we will have, which is this edge, we will have a tail. This is the tail. A would be the tail, and D is the head. So imagine that we have a sort of bird laying on this with the body on this edge, and the triangles which are containing this edge will be its wings. So its left wing, if this is the head, so I will draw here a little head so that we can remember where is the head. So the left wing will be the face which is called 3. You see, it is pointing, it's the back face, and it's the left wing. The right wing will be the face 0. So this is the left, this is the right. And now, so we have already, with you can see, we have a tail, we have the head, we have the left face, which is number 3. This here we have the right face, which is number 0, and now within the left face we are looking for previous edge. So that's here. Previous edge counterclockwise would be, well, we need to, this is a back face, therefore we need to turn ourselves so that we are looking at the back face directly, and counterclockwise the previous edge will be the F. So this is the previous edge counterclockwise. This is the A will be the current edge, and the next edge will be E around this triangle. So we have these two, and now we have also for the right. Now this is easier to imagine. Previously is which edge is here in the counterclockwise way? Well, it will be the C, because C counterclockwise to A, counterclockwise to successor B. So now we understand this complex storage of this winged edge mesh structure. And based on this information, we are able to now find all the necessary information we would be interested in. In addition to the edge data structure, we will have the vertex data structure, which the vertex will be associated with a with any edge which is going from this vertex. Similarly, we will have also the array of faces where we will store one edge which this face consists of. With this winged edge mesh structure, we can now easily calculate the all edges of a particular vertex. Let's have a look at how this can be done. So at the input, we have our vertex V, and as we know, we are storing one edge which is containing our vertex V. Let's say that this is our vertex A, and the stored edge corresponding to A is, as shown in the previous slide, the edge A. Now, we are again entering a loop where we will find all the necessary edges besides the A, which is already explicitly given. So we have an A, and now the question is the A tail of E or is it the head? Well, we know that this is in the edge structure. Here is the tail, here is the head. A vertex is the tail. So yes, it is the tail. Therefore, our edge, next edge, which belongs to, which contains A, is stored in the left previous. So left predecessor will be F. Left predecessor is F, and that's true. This edge certainly contains A. So we have done that, and now our current edge is F. We make one more loop, and now we try to find out whether, again, of F, A vertex would be the tail or the head. So let's have a look at the row F. Well, here the A is actually the head. So we need to go into the else, and we are now setting the edge into right previous. Right previous of F is face right previous would be the B. Okay, so we have the B, and we have now found all the three edges of our vertex. Now, are we now stopping? If we are now having our edge will be B, then is the A vertex the tail or is it the head? It shows it's a tail. Therefore, the next edge should be stored in the left previous for the edge B. Left previous would be A. And now we have the condition, is the edge, which is equal now E is equal to A, the edge associated with the vertex. Remember, that was the one we started off with, which was equal to A. Yes, it is. Therefore, we are stopping the loop because we have found all the edges which are associated with the vertex A. Now, how do we find edges of a particular face? So if we have a face, and allow me to delete now so that I can make the entries again. The code will, at the input, we have our face F. The face F, let's say that our face F will be the face 0. And the associated edge with the face F, which is the face 0, is the edge A, in fact. And now we can enter our loop to find all the other edges which are forming our face 0. So if E left is equal to our face, so E left, this is if A dot left is 0, let's have a look. A face left is not 0, therefore we go to the else. Else is equal to E R next. So what is stored in the right next? Successor right is B. So the next edge of our face 0 will be B. Correct. This is the case. And now we make one more loop for B. If B dot left is equal to 0, B left is equal to 0, yes, this condition is fulfilled, then the next edge is L next. So that will be the edge C here, which we see is correctly determined. And again, once we have the third edge C, we could already know that we have found 3, so we could stop. But actually, we can find out whether we will stop at this condition. So C dot left, is it equal to 0? Face left, yes. So the next one will be therefore E L next. C is next L, next left, will be the A. Therefore, the A is equal to F E is equal to A. Therefore, we are stopping in our loop. This structure has the advantage that it doesn't only work for the triangles, but actually for polygons in general. So this might be handy, although we could, after 3 iterations, automatically stop for a triangle. If we have polygons, we will have more iterations to perform. Our weak edge mesh structure has just one disadvantage, that it can be mitigated with the following optimization. It contains a conditional. For each edge, in previous codes, we always had the if statement to find out whether our vertex is, which we currently have, is the edge's tail or is it edge's head, or whether the face which we are processing is having its left face of the edge or the right face of the edge. And now imagine that we dissect this weak edge mesh structure and we create 2 structures out of one weak edge mesh structure, namely 2 half edge mesh structures. In this case, our half edge will be oriented in one direction and it will be pointing to its head. It will not store its tail, and it will be pointing to the next edge within a triangle. Also, it will be pointing to its left face, as we can see here, and also it will be pointing to itself, to the second half edge of that edge. And that one will be storing again its own head, its next edge for that face, and the face on the left from this half edge. With this separation of one winged edge into two half edges, we can get rid of the if conditional. Let's have a look how we can calculate the edges of a vertex or which edges constitute a face. So we can see that we have here the data structure half edge, and for each half edge we are storing its pair and the next, as well as the head vertex and the left face. We are also storing having the vertex structure, which will be containing, besides other things, the half edge. And we will also have the face structure, which will be containing the half edge, one of the half edges which constitutes this face. And now, once we have this vertex, for a particular vertex we are interested in, we can find out what is its half edge, because it's stored there. And with this half edge, we store it in the h variable here, and then we know this is one of its edges, and we need to find all the other edges. Well, for the vertices, we do not know how many edges there are, but we will find it out through a loop until we find again a half edge, which is the half edge stored in the vertex. So, and here you have a slight difference in this code. In the book, there is the next and pair is switched, which would not lead to correct algorithm. So here we are in the loop. We will be storing, and allow me to clean this up for you a little bit. We will be storing we are looking for the next half edge will be the next edge, so it will be this edge, but it's pair, because the next edge is having his head in this direction, that's why we need its pair. And then, again, the same will continue again and again. Let's see an example of it. Let's consider this point be our vertex, which we want to rotate around, and it has its associated h0 will be the half edge which it stores. The next half edge will be the h2, however, we want really its pair, which is the h3. And then the next one will be the h9, but again, we want its pair, which will be pointing to the next half edge, and so on and so on. So we are always interested of the pair of our edge, which is stored as the next. The next will be directly interesting for our searching for the edges of a particular face. So again, we have one half edge stored for a face. Let me again delete this. And so let's say which could it be? Let's say we say that our face, this is the face we are interested in, is storing our the half edge will be h0. And then its next will be h2. So we are then calculating the next half edge, which is the h2, and then its next half edge will be h5, and its next half edge will be again the h0. So this way we can easily make a circle around the half edges to find out all the edges of a particular face. And if we want to know both vertices, for example, of the edge, then we can take the head vertex and the head of the pair. So this data structure would be the fastest to calculate because it doesn't have any conditionals, and we can directly compute the next step around a particular vertex or edges of a particular face. The mesh is organizing triangles of one particular object, but we have higher level organizations in the scene which we need to care about. Scenes are often organized in hierarchies. For example, if we think of a human body, we can have a model which contains its torso, which contains its head, which contains its upper limb, which would then consist of several subparts, like, for example, the hand, which consists of fingers and a palm. So we can see that there are a lot of hierarchies, and for performing a transformation of such a hierarchical structure, we can take advantage of these hierarchies. So, for example, let's have a look at this pendulum shown in this image here. We have two parts of the pendulum. The blue part is the lower part, and the upper part is the orange one. And the transformation of this pendulum will be to first, for the upper part, which we call parent now for a moment, we will explain why. It's we first perform the rotation around its around the origin by the angle theta, and then we translate it to a certain point P. So we have, this was the origin position. First we rotated it slightly by theta, and then we translated it here. Now, if we want to perform a transformation of the second part of the pendulum, this blue part, we want to also rotate it and translate it, but we rotate it by an angle phi, which is an angle from which is a partial angle of rotation, and then we translate it to the point B. The point B is this point here, which is at the end, lower end of our upper part of the pendulum. So these were the two transformations we have done. And in order to have these two parts of the pendulum connected, we can see that if we perform first the child transform, we rotate it slightly by phi and translate it, we will get it slightly rotated into the position B. So it will be connected with our upper part of the pendulum. And if we, for both of these parts, then apply the operations, which is called here M3, which consists of M1 and M2. So M1 and M2 is equal to M3. Then we will be transforming both of these parts together. So for our parent, we want to perform an operation which is just the M3. This is for the parent, which is the M1 and M2. And for the child, we want to perform operations which first the MC, which is the MA and MB, rotate and translate, and then the operation which is the MC, and then the operation M3, which we did per parent. So this is the complex operation for the child. And we can see that the M3 is part of the transformation for both of these parts. But simply the child has more transforms to perform. But this is the way how we can concatenate various parts which are hierarchically organized in a scene in the so-called scene graph. And this can be realized by the following push and pop operations, which can push matrices into the stack. So we can always, if we push a matrix, we will push it on the very right side. If we will now, from the stage when we have just a matrix M in a matrix stack, if we perform push, then the M1 will be on the right side. So it will be performed first. So we can now have a look at this example, which is shown here. This example shows a car which is having two wheels, and it has a this car is also located on the ferry. And for the ferry, we only have one transform. It will be maybe some translation which moves our ferry. And then on the ferry, our car can move, but together with the ferry, it will move even by the matrix M0. So the transform for the car will be M1 and then M0. And for the wheels will be rotating. So for them, we will have additional transforms. So for the left wheel, as it is written here, it's really a rear wheel, right rear wheel. We will have the additional transformation M2, and for the front right wheel, we will have the additional operation M3. Please keep in mind that there is a typo in the book, and there is twice written left. So once it is meant right, while it really means front right for the car. It's just in this projection, it is on the right hand side. And let's have a look what is being performed in the scene graph with this push and pop. So if we have a particular node in our scene graph, which is really a scene tree in this case, so we can see how these hierarchies are organized. So this is the level 0, this is the level 1, and this is the level 2. So level 1 will have the children in the level 2, and level 0 will have children in the level 1. And we can see that if we want to perform certain transformation, then we first push at the beginning our local transformation. Then we perform the transformation from the composite matrix stack, and then we we recursively traverse this tree for the left child and for the right child. We might have more children to traverse, but in this case, it will be just these two. And then in recursion, the same operation, the push operation, will be there, and they will push their own local transformations. Once we dive out from the recursion, we pop so that we can perform the so that we can free up, delete the local operations which were there performed for the children and for our current position. Structures like scene graph help us to manipulate the scene, which is hierarchically organized in a logical and intuitive way. We have other data structures, spatial data structures, which are also of a hierarchical nature, but those are often meant for handling complex scenes so that we have faster access to the individual elements, and the complexity is reduced from the linear complexity of traversing through all the objects when searching for a particular one, such as intersection with it, to a sublinear complexity. And this is often done with a divide and conquer strategy, which is a very natural choice for dealing with some hierarchically organized data. We will be talking about various types of data structures, which are either object-centric or scene-centric, and are partitioning our representation so that we can quicker evaluate whether we are supposed to handle a particular object or not. We will be exemplifying this on the ray tracing example, where we need to evaluate the intersection test with our objects. However, it could be used for any other purpose where we need to access our objects, and without any additional structure, we will need to proceed in a linear fashion. So our scene can be organized in such a way that we are clustering or organizing our graphical elements or geometric elements into some sets that are enclosed in a representation that is easy to compute, such as, for example, the bounding boxes. With bounding boxes, what we are doing is we are enclosing some part of the scene so that we can quickly evaluate whether this part of the scene will be or will be not interacting with our ray in case of ray tracing. So you can see here that the gist of the idea that instead of dealing with 1, 2, 3, 4, 5, 6 different triangles and evaluating the intersection test with these triangles, we are simply just evaluating whether this ray is hitting particular bounding box or not. And as we find out it's not, we therefore, as this is a superset of our triangles and enclosing structure, then we can immediately discard and do not need to perform any intersection test with these triangles. We will exemplify so-called axis-aligned bounding boxes now, and this will be done on a two-dimensional case. The three-dimensional case is pretty straightforward and analogous. So we can define our bounding box by two parallel sets of lines as one set of line which is in the horizontal direction, and another set of lines which are in the vertical direction. And the space between these lines is forming our two-dimensional bounding box. Therefore, for an intersection test with a line, we have quite a simple way to finding out whether we are intersecting the line or not. Let's have a look at the description of a line intersection test. So that will be that some x, I call it min for a moment, which is not important, y, for the very second, is equal to x, xe plus t min times xd. So this is the direction of the vector, this is the I point, and we are traversing to find the intersection test. And the x-mean will be the intersection with the smaller, with the, so to say, the first horizontal intersection. Now, we can reformulate this equation trivially into this equation to find out the Tx min. So sorry, this here should be x to Tx min, and we can evaluate this intersection. Similarly, we can evaluate the intersection with the second line which is parallel to it to find the Tx max. And so we will have the Tx min and the Tx max in one dimension, and in another dimension we will in exactly the same way compute the Ty min and Ty max. You can already imagine that for the third dimension there will be a z component too. And now we are simply having intervals of t, and the interval of t needs to be between the Tx min and Tx max, and Ty min and Ty max need to be a non-empty set. If that will be the case, then we have an intersection with the bounding box, and not only with these lines outside this bounding box. So we can see it nicely shown in this drawing, where we see the interval of Tx min and Tx max, and then the Ty min and Ty max. And we see, oh yes, they are not by much, but they do overlap. And as we have this overlap, then we have to conclude that yes, this bounding box is being intersected. There is some part of the ray which is going through it, so we have to check the objects which are enclosed by this bounding box. However, this was for in case the xd is positive. If the xd is negative, meaning that we are our array goes in the x direction, in the negative x direction, then we have to do some simple switch in order this to work. So we will first hit the x max and then the x min in such a case. So if xd is bigger than 0, then so it's positive, or 0, then, which 0 would not make much sense, but positive, then the order is the same. For Tx min, we are using the x min. For the Tx max, we are using the x max. However, if we are having the negative, then we are first intersecting the x max line. So we store this in the Tx min, and the same holds for the Tx max. Then we are using the second line, which will be the x min line. And then we are proceeding exactly as we did in the previous case. So we are just fixing our order by this if-else statement. And this holds for the x-coordinate, and very analogous operation will be necessary for the y-coordinate as well. Bounding boxes are, as described now, have been only described as an axis-aligned bounding boxes. So in case we have our coordinate system and we have certain objects, then we will find their borders in one dimension, in another dimension, and this will be the enclosing structure. However, this might not be optimal for every geometry, and we might have a problem with, imagine if we have such an ellipse or ellipse-like structure, then we will have a lot of space which we will need to, which our bounding box will be spanning. So for many rays, we will have a false positive, meaning that the rays will be just passing through this area, and we will not be hitting the ellipse, but we will be always hitting having an intersection with the bounding box. Well, this could be partially circumvented by a more well-aligned bounding geometry, which is called object-aligned bounding boxes. And the object-aligned bounding box will sort of evaluate what is our main axis of the object, and will align the bounding box with this main axis, and will try to fit much better the box around the object than the axis aligned bounding boxes. This would be great, and in such a case we will need to evaluate an intersection test with not such easy lines as in the previous case, but a more difficult description of a line, but still not very computationally expensive operation. And if we will be dealing with a three-dimensional case, there will be no lines, but there will be planes, and we will need to evaluate whether our array is having an intersection with these planes, and whether there is an interval which is for all planes, so to say, inside the bounding box. These bounding boxes do not need to be organized on just one level. We can have a hierarchical bounding boxes. So meaning in case we are having a positive test with one bounding box level, we can still check whether we do have a positive test with one of its children, which are subdividing the scene gradually, so that eventually we will then have just a few simple geometries enclosed by a bounding box. Please note that these bounding boxes are defined on a per object basis. So we define that we have certain objects, like these objects here in the light gray, and these objects have because of these are axis aligned bounding boxes again, because of their extents, the bounding box looks approximately like this. And if we choose these other objects together forming a cluster, then their extents will define a bounding box, and these two bounding boxes are overlapping, which means that if we are performing a test with a bounding box, we are only relating to those objects which are stored or which are members of that bounding box. But it might mean that there are also other objects which are within the bounding box, but that test is not giving any particular value to our to those objects. Let's have a look at this particular case where we have just two-level hierarchy. So we would have this thin line as one bounding box, and then this bounding box will have two children with a more thicker lines, which is this one and this one. Well, this code piece here is just describing this particular case, but we can imagine how this could be generalized for a more general scenario with more hierarchies or with varying levels of hierarchies. So, and As we are dealing with trees, in such cases, often a recursion is the method of choice to solve these problems by the means of a divide and conquer. So this code starts with if we have hit the root box, so the thin box which is around our two thicker demarcated boxes. If that's the case, then we need to check whether one of these two boxes will be intersected. If this is not the case, then we can immediately return false. So we early can terminate this process. But if we have a hit, we have to check whether there is a hit with the left subtree. And then if that's the case, then we need to check with the triangles which are members of this or are grouped in this bounding box, whether there is an intersection with them. Then we continue. Even if there is, we have to continue with the right subtree and check whether there is an intersection. And the intersection which is returned from both subtrees, we need to return the one which is the closest of the two hits, meaning that the one with the lowest t value as the parameter in this parametric form of array. And if there is only one intersection returned, well, then we take that intersection and evaluate, and that will be the intersection with our array. And if there was no intersection, then we missed it. While we hit the above box, we didn't hit any of the child boxes. So you can imagine that the ray was passing like, oops, this would be actual hit, but it will be passing like something like this through our boxes shown here. We call these organizations as bounding volume hierarchies. It is often abbreviated as the BVH, which you can find in the computer graphics literature. And it refers to various bounding hierarchies. It might be hierarchies created by spheres, because sphere is a very simple object to make intersection test with, or it could be the bounding boxes, or it could be maybe an ellipsoid or object aligned bounding boxes as well. So these bounding volume hierarchies, before we can actually execute a code similar to the previous slide, where we are checking for the intersection, we need to build them. And how can we build these hierarchies? Well, it makes sense to create the hierarchy out of our triangles in such a way that we are roughly separating it into two parts, because let's say the bounding volume hierarchies will be a binary tree where we have a left child and a right child. And it, of course, doesn't need to be spatially left or right. This is just a conceptual binary tree where one child is called left and another one child is called right. So let's have a look on an organization of the bounding volume hierarchies. And this organization is often done in such a way that we choose one axis within our space. So let's show this on a two-dimensional space, and we have our objects stored here. And we take first our x-axis, and we will simply store our objects in the or partition the scene, the objects along this axis. So we will find out along an x-axis if we want to have a balanced representation, that we have 4 objects, so we would like to create the bounding volume hierarchy for 2 objects being the left and 2 objects being the right children. Well, we might still change the direction in the second pass if we want to create more volume hierarchies and now try to organize the split in the along the vertical axis. Then we can find out that we can further split the group into 2 parts, where we will have then, this will be then the LL, this will be then the LR, and this will be then the RL, and this will be then the RR, if I should use this terminology for defining the children in the second level. So, and generally a scheme where we are looking at how many objects do we have, and then half of the objects along that axis will be forming one partition, another half of the objects will be forming another partition. And this is the corresponding pseudocode for that, because you can see that we have some object array and we have a given axis along which we would like to perform the partitioning. And if we just need to check for some simple cases first. So if we have our object length is 1, then we simply are putting one child into left and right will be now. And then we will be generating a bounding box just out of this one object. If we have 2 children, then one goes to the left, one goes to the right. And then we create a combined bounding box out of the bounding boxes of these 2 respective children. And here we have the sort of the most common case where we have more objects, and then we take half of the objects to be forming the left children, and the another half will be, so this is one half, as you can see, this is another one half, as you can see, and we are calling recursively the same function, and we will be splitting these objects with another axis. So if we started with axis x would correspond to 0, y would correspond to 1, and z would correspond to 2. So with this, we will be then looping, and in always the next case, we will be partitioning along a different axis. And once we perform our partitioning, then we always combine the children's bounding boxes into a bigger bounding box, which will then be used for the current level. So this is a way how we can create the bounding volume hierarchies, and then we can traverse them in a similar way as we have seen in the case of the simple scenario on the previous page, pseudocode, and in a general case, we will be using also recursion for this traversal. Alternatively, we can use other form of partitioning in such a way that we will not be performing any sorting. So we will, in the previous case, we had to sort the objects along one axis and then take first half into one child and the second half into another child. In order to avoid the sorting, what we can simply do is to look at the min and max in each dimension. This is the else part, which would correspond to here. And then when we know the min and max, we will simply take the midpoint and every object which is before the midpoint will go to the left child, and every object which will go to which will be having higher value than the midpoint will go to the right child as a partition. This will result into a not so balanced tree, because there will be not half, and the tree will be slightly unbalanced, because this way we cannot control how many elements are in fact in one or the other side of the binary tree. So it might be that the objects will be more towards on the right side of our midpoint, because there is an outlier on the left which is skewing the average midpoint calculation, and that's how we will get to a less balanced tree, which will be then probably less effective for the array traversal during the rendering. So, but the generation of this tree will be likely cheaper with the partitioning. Now, this was then an approach where we were organizing our scene into hierarchies so that we can traverse the scene by making tests, intersection tests, which are much cheaper than the test of the entire set, which these super objects, proxy objects, bounding objects are covering. This is one strategy where we are somehow partitioning, subdividing the sets of objects, and for them we create these bounding geometries. But we can as well subdivide the entire scene or space. So instead of being object-centric, we can be scene-centric and have a uniform space subdivision, and just check within each of the cells of this space subdivision whether there is a certain intersection. This would mean that we will, in each of these cells, store information whether an object is present, at least partially, in such a cell. And if that's the case, then we are intersecting this cell, then we will have to check for a more thorough intersection with the actual object. We see immediately on this image shown here the advantage. While we have the entire scene here, we can immediately disregard a lot of space subsets, if you like, in our calculation, because they will simply not be intersected by our array. And those who will be intersected, we check whether there are any objects. And if there are no objects in those subdivided spaces, then we can skip them quickly. So, and the idea is that as with the axis aligned bounding boxes, it is very easy to calculate the intersection and generating this T min and T max, and in the X and Y direction, we can do something similar in this space subdivision, because this space subdivision will be also aligned with our coordinate axis. So how do we proceed with the uniform space subdivision? Well, we can see that for a particular array and for a particular subdivision scheme, we see that there is a lot of intersections with our cells. And these intersections, at the first glance, they do not look very well organized. However, and this is obvious to us, if we look at a single direction of our space partitioning of parallel lines or planes along one dimension, then we see that those intersection points are actually equidistant, and we can very easily find out if we know what is, let's say, this t for our parametric ray and this t, we can easily find out what will be this t without making the intersection test, because it will be just the same distance. So we can just find out the increment to find out what will be the next t value of intersecting the next level of in one particular direction. And the same holds in the other case of other dimension, other coordinate axis. So we have again also equidistant intersections because this space is subdivided equidistantly. So this means that we can simply have two arrays of t's in 2 dimensions. In 3 dimensions, it will be 3. And we can always search within the arrays of t's, which is the smallest one. And that one will define whether we are moving, how are we moving within the cells. So we want to find out whether our next cell will be sort of increment in the x dimension or y dimension or both dimensions within our this coarse space subdivision. And the t value will be telling this to us, the t arrays, because we will be always searching for the t minimal. Then we process it, we find out which cell does it enter. Then we look for the next t, which will tell us where the cell is being to be exited. And then we look for the next t of the intersections in both of these arrays in 2 dimensions to find out which cell we are then passing through. So this way we can quickly find out what are the intersections of our within our cells, which cells are being intersected, and then we process in case we are intersecting the cell, then we are evaluating which objects, whether there are any objects, and if there are, we will have to evaluate which is being intersected. We have here one example case where we might have sometimes an strange scenarios where, for example, we have a primitive which is part of our cell through which our ray is going, and we will then therefore we are intersecting this cell with our ray, and we are also having one triangle there, and then we check for the intersection, and we indeed intersect with this object. But we have to be careful because this object has been intersected outside the cell. So if some object is part of the cell, it doesn't mean that it's only stored in that cell, but it could be that it is also expanding beyond the cell borders, and there it can be intersected with the ray as well. We need to check for that. Another popular representation for space partitioning next to the uniform space partitioning is a binary space partitioning, where we will again be forming hierarchies of space partitioning so that we can evaluate whether there are objects inside which are intersected with our ray. So we can imagine that we might have, for such a scenario, you can imagine that we are first partitioning along one axis, then in the second level of partitioning we will be partitioning along another axis, and so on. But we will not be generating bounding boxes. This space subdivision is forming this bounding representation, so to say. And if we have array, we have to evaluate, again, this will be this space partitioning is binary space partitioning, and it's again often abbreviated as BSP. You will find that in the computer graphic literature. And here we have 4 scenarios we should consider given a particular binary partitioning on any level within our hierarchy. So we have a case where our array is going away from our partitioning element, should it be a line or a plane. So, and it is starting within the left child. Here the left, in this particular case for the X dimension, will really mean left child. In other cases, it will not, the left meaning will not have the same meaning, but it will be still a geometric partition of the scene, not a grouping of objects, but a partitioning of the space, so to say. The second case we have is where we do start from the left, in the left child, in the left subspace, but with our array, we will be going to the right subspace because it is oriented so that there will be an crossing of our partitioning border. And therefore, we would need to check for intersections in both subspaces for the case 2. Case 3 is analogous to the other case already explained, and case 4 is analogous to the case 2. It's just from the right child, so to say. It is described here as the descriptions of the XP and XB, where the XP is the x-coordinate of a point on the array, and the XB is the x-coordinate of the vector along which the array goes. So in this case, the XB is smaller than 0. It is negative because it goes towards the negative x direction, and XP is smaller than D. The D is here where our border structure is at the particular distance D. So from the coordinate origin. So if the XP is smaller than D, then we have the case 1, and the XB is also smaller than 0, then we have the case 1. If we have the case where the XP is smaller than D, but XB is bigger than 0, then we have the case 2. And then if the XP is bigger than D, so here the XP is somewhere, and the XB is bigger than 0, then we are having this third case, and if the XB will be smaller than 0, then we have the fourth case. And now we are evaluating what should we do in a pseudocode as was described by words so far. So we can see, and here we only show the 2 cases because there is only the pseudocode for the 2 cases shown, but the cases 3 and 4 will be analogous. So we have our binary space partitioning, and we are evaluating whether our array is being intersecting this space and whether there is any hits. So here is our definition of the line, where the A would be the starting point and the B will be the vector, the direction of the ray. And we are evaluating, so that we can see it, we are evaluating whether XP is smaller than D, as we were discussing to find out the case 1 and 2. And if the XB is smaller than 0, then return true in case left is not null, and at the same time there is a hit reported by the recursive call. So you can see that this function returns a Boolean value. True will be for hit, and false will be for not hit. And in case we have a hit from the child, then this will be then returning true here. Also for this node, so to say. If the XB is not smaller than 0, then we are proceeding further. And in this case, we first need to calculate the T, which will be the intersection with our partitioning geometry, in our case, the line x equals D, and we need to find out what is the value of the parameter T at this intersection, because we need to then evaluate our intersection on the left side with a smaller interval than the previously defined interval of T0 to T1. We find out whether our T is bigger than T1. So we are only interested in intersections in this interval of T's. Therefore, if the T will be bigger than the T1, we are not really interested in anything for T is bigger than T1. And therefore, we will again execute a return of this function with calling the left hit on the original interval T0 and T1. If this is not the case, where the T1 will be indeed behind the x equals D, so to say, then we will be evaluating and on the left side only hit between the T0 and T, and if this will be both true and the left is not equal to null, then we will return true. However, if this will not be the case, then we are simply returning the intersection with the right side, so to say, where the x is bigger than D. So then we check whether right is not null, and then we perform the hit routine where our interval of T is scoped from T to T1, because the T is the T parameter where the right side, so to say, starts. For the cases 3 and 4, this will be analogous. It would mean that the XP is bigger than D, and we can see that a very similar code can be then generated for these analogous cases too. The BSP, binary space partitioning, is not only performed for the space partitioning for ray tracing, but also for evaluating visibility. The difference to the axis-aligned BSP operation is that in the previous case, we had the space partitioning axis aligned, And the BSP trees for visibility are in fact using the geometry itself for performing the visibility test. And this is done on a mesh structure, so on a scene representation by triangles, where we can define a triangle, and this triangle will be then defining as a plane, and this plane will be serving for space partitioning the scene into what is in front of this triangle plane and what is behind it. And naturally, if we want to then perform the rendering, those things which are behind can be rendered first, and then they will be overdrawn by the structures which are in front of our triangle plane, which is partitioning the space. The basic advantage over the standard painter's algorithm, which will simply sort all the graphics or geometric primitives and then draw them in the back to front order, is that here we have a structure which allows us to perform the drawing without any sorting. So we will generate the BSP tree, which is view independent. We will partition the scene based on the triangle's planes into front and behind, and then we can, in a recursive manner, subdivide to higher and higher details of our scene. So eventually we will be deciding whether an triangle should be rendered first, then the triangle which is forming the plane, or the triangle forming the plane should be rendered first, and the other triangle should be rendered afterwards. And this is all view independent because we can evaluate the position of the triangle with respect to the plane of the partitioning plane defined by another triangle, and we can evaluate whether it is in front and whether it is behind. And the same we can do also with the viewpoint, with the eye point. So the principle is that our triangle will define a plane, an implicit equation of the plane, and this implicit equation of the plane can simply be tested whether things are in front or behind it by putting the points, coordinates of our triangles, so A, B, or C vertices of these triangles, and evaluate whether it is bigger than 0 or smaller than 0. And the same we do for the eye point. And if our tested triangle is with the same sign before, so to say, or after both this plane, then it means that the triangle which is defining the plane should be rendered first, then the triangle which is on the same half space, so that the eye sees these triangles orders in the correct way. These BSP trees for visibility are naturally oriented for rasterizers, because we want to know for rasterizers which triangle should be sort of rasterized first before another triangle is being rasterized. So here, how do we proceed? Let's have a look at this scenario where we have one triangle, T1, which is defining as the partitioning plane, and then we have a triangle 2, and then we have the eye point. Obviously, the triangle 2 and the eye point will have different evaluation. One condition which we want to take care of before we do any further processing is that all the points of our triangle are in the same subspace partitioned by this particular partitioning plane. If this is not the case, then we will need to subdivide this triangle into smaller ones so that there will be always just one subspace occupied by, or the triangle will be located only in one of these two subspaces. So let's say we have the scene prepared in this way. And how do we then perform the rasterization? Well, I mean, if the tree is empty, then there is not much to do. If we evaluate our function of our plane and with respect to the eye point, we find out that this is the sort of first partitioning. We find out that the eye point is on the negative side. For example, in this case, if this would be true, then what should we do first? Well, then first draw the everything which is in the positive side. So this is plus, this is minus. Then rasterize the tree triangle, which will be our T1. And then draw everything which is in the negative subspace spanned by this or defined by this partitioning plane. So we are recursively calling the same function again, but only to a limited spatial extent. If this is not the case, meaning that the eye point is in the positive subspace, so this is E is smaller than 0, and this is E is bigger than 0, not the E really, but the F E, the plane function, implicit equation. And here then, what we need to do? Well, again, we need to draw everything which is behind that plane. Then we rasterize the plane and the triangle which is within that plane. And then we draw everything in the positive part of the partitioning. Let's have a look at this scenario. How does such a space partitioning look like? Well, here we have two triangles which are partitioning our space, and two functions, f1 and f2, which are the implicit formulas or functions for the planes defined by our partitioning triangles, T1 and T2. Well, our T1 is the first which has been selected for the partitioning, and for that one, both the T2 and T3 are on the positive side of the T1. So they are not behind the plane, they are in front of this plane. As we can also see, this plane is somehow here. So our triangles are in front of it. Then, so we do not have anything on the left side. We have only positive, some elements in the positive subspace. And then we have the T2 as a partitioning triangle, and that one is partitioning the space into two half spaces, and our T3 will be in the negative half space with respect to T2. So we already see how this space partitioning will generate us this tree defining what is in front and what is behind. And as I said, if there is a case where this is not equally valid for the entire triangle, then we will need to split the triangle into smaller triangles. Let's have a look how we can build such a tree as it was indicated on the previous illustration on the slide before. Well, imagine that we have several triangles to deal with. Therefore, we will be adding these triangles either to the left or to the right. So we are evaluating for each triangle what are its values of its vertices, and if they are all negative with respect to a certain root or local root, so to say, then we will be adding them to the negative subtree. So if the negative subtree is empty, then we simply assign this node to the negative subtree. Otherwise, we add this triangle to the negative subtree. And if all functional values are positive, then we are adding our the triangle to the positive subtree, or we are defining it as the positive subtree if this was empty before. And otherwise, it means that there are triangles for which there is a mixed sign between FA, FB, and FC, then we will need to do something else. And we have assumed that this case is impossible, so that there has been some subdivision of such problematic triangles happening before. How can we split such a triangle? So if we have a partitioning plane and our C is, for example, on one side and AB is on the other side, well, we need to evaluate what are the intersection points of our edges on this plane. And well, this basically is a question of having a parametric line description from our sides, like for example the edge AC, and we are trying to find out the t for which the value of our function is equal to 0, of the function of our implicit plane. Our implicit plane equation is of this form, as you remember. So ax plus by plus cz plus d equals 0. And you remember that a, b, and c are forming us, in fact, the normal vector to this plane. And x, y, and z are the coordinates of points. And if this is equal to 0, then these points lay on this plane. Therefore, we just plug in our parametric definition of our ray into this equation and then define what is the t for the value 0 of this implicitly defined plane. So, and from that, we find out that this is the formula which defines us the t, the intersection with the plane where the intersection point is happening of the edge AC. So we will be finding basically a point capital A here, which is the point on which the plane is being intersected on the edge AC. This can be easily defined as point A plus TA, the parameter which we just computed, and the vector AC, which we can easily calculate. Now, the same we can do for the B, and based on the BC, edge, and then we have our intersection points. These intersection points we then use for our subdivision. So we would like to have one triangle, which will be the capital A, capital B, C, and the other triangles will be then A, B, capital A, and B, capital B, A. And we can see that this is indeed, I'm sorry, this is indeed the case as shown here. This is the desired subdivision, so that these both triangles will be in one subspace, and the triangle capital A, capital B, C will be in another subspace with respect to this partitioning plane. One aspect which is worth mentioning regarding the subdivision is that the traversal of our scene, in order to be able to draw the subspaces and eventually the individual triangles, is dependent on how many triangles we have in the scene. Therefore, it is actually not good if we need to perform the subdivision of a triangle into 3 other triangles too often. This, of course, will be dependent on which triangles do we choose for the space partitioning, and some of them might actually define the plane where no such triangle subdivision is necessary, and others will be requiring this. Therefore, there will be a good heuristic needed in order to find such space subdivisions which will result into reasonably few not space partitionings, which will result into reasonably few subdivisions of the triangles. So this is all for the binary space partitioning for the visibility. Our last focus of data structures for graphics will be for tiling multidimensional arrays. Two-dimensional images or volumetric datasets are both good examples of multidimensional arrays of values which we would need to deal with quite often, whether we are using it for texturing or for solid texturing or for other purposes. We often need to deal with multidimensional arrays. These two-dimensional or three-dimensional arrays have a certain neighborhood around their sample points, which they store in 3 dimensions or in 2 dimensions. However, our memory layout is one-dimensional. That's not a conceptual problem in itself, because we can always convert a multidimensional array into a lower dimensional one, simply unfold it, so to say, and so the indexing will work. The indexing is described here. You can imagine if we have a 2-dimensional image, which will be like the number of elements is in the row is an X, and the number of rows will be n Y. Then if we want to fetch a particular value X, Y, then in the 2-dimensional array, if we have all this information stored in the 1-dimensional array, we can simply convert it in this formulation. So we are multiplying with number of the length of a row and X with the number of rows which we fully need to sort of pass through, because the storage is linear, one row after another. And then we need to add the additional X values to it to reach our point XY. This is not a big deal, and we can easily do that also for 3 dimensions. So it will work. But as we have one-dimensional alignment, our cache in the memory will also be aligned with this one-dimensional layout, meaning that if we will be fetching some elements from the same row consecutively, then we will probably be able to take advantage of cache coherency. But if we would like to explore the neighborhood of a particular sample, then the problem will be that in one direction we will be able to exploit the cache coherence, and in another direction we will not. Or in case of 3 dimensions, we will be able to exploit the coherency only in 1 dimension, so to say. And if we are computing derivatives or other information, convolutions, other information from the neighborhood of our sample, then we will be suffering from this unbalanced cache, this anisotropy of this alignment, which comes from the conflicting scenario that our memory layout is linear, while our objects in the scene are 2 or 3 dimensional. We can see here that on a tangible example, where we can see that if we have an 0, 0 point, then this 0, 0 point will have, upon fetch, will likely fetch also the point at 1, 0, and maybe 2, 0, but the point at the point at 0, 1, this one will not be fetched with the texture fetch, and that's kind of a problem. We would like that the entire neighborhood of our object is somehow stored close to each other. And that exactly is what the tiling or bricking is doing for us. And we can see it on the example here, where we are sort of having a coarse level bricks over our finer structure. Maybe you can talk about the different scale of indexing in some sense, where you see that the 4 elements next to each other are next to each other also in the memory. So in the memory, the layout will be, this will be the first element, second element, third element, fourth element. And then the memory continues here, forming another brick, and so on, and so on. So we will have a great ability to exploit the cache coherency within the values of a brick, but outside, even if they are close, there will be no likelihood of a high cache coherency exploitation. And that's, of course, as far as we can go with trying to pack the neighborhood of 2 or 3 dimensions into 1-dimensional organization. So somewhere we will have to have a border of our bricks, and across this border there will be no exploitation of the coherency. So how does this work? We define the so-called bricks upon our array, and you can see here the example of our array, which is shown in this fine grid. So these are really our data points, and the other data points are also here and in all other bricks, but they are just not shown. What we want to, what wants to be shown in this image is that we have n times n large brick, so n squared elements are fitted into one brick. And how we can compute, therefore, the number of bricks in 1 dimension, in the x dimension. So how many are there? Well, if we have our entire amount of elements in the row, and we divide it by 1 brick size, then we get the number of bricks in 1 dimension. The same holds for the y dimension, where we take the number of rows, if you like, and y, and divide it by the size of a brick, and then we get the number of, so size of the brick, we get the number of brick in the y dimension. If we want to perform a certain brick indexing, so in which brick we are, we can use the integer division, where we divide our x coordinate of our xy two-dimensional array by n. And then we get to the beginning of our brick, which brick in our x resides in. So say if we have an example that x is, let's say, 15, and our brick size will be 4, then our in x dimension and y dimension, let's say also 4, then our element will be in the 15 will be in the third brick and one of the last elements there. Sorry, I mean fourth brick and one of the last elements there. Okay, so we can calculate the brick index in x dimension, we can calculate the brick index in the y dimension, and we can also calculate the index to the first element within a brick. So that can be calculated in a similar way as we were performing the indexing as for the regular linear layout, meaning that we multiply the number of y with the number of elements in the row, in this case number of bricks in the row, and plus the offset of the in the particular row. In this case, this is not the element x, but this is the brick within several elements are then stored. In order to be able to get to the first element, we have to multiply that number by n squared, because here we are really operating on this Horst scale. So we will be having the same indexing on these big pixels, so to say. This will work exactly as we had in the previous slide. And if we multiply it with the n squared, which is the size of the brick, then we will get to the actual element in the more finer scale, the first element within the brick where our xy coordinate resides. And once we successfully calculate the first element of our within the brick, then we need the partial offsets in the brick in order to be able to address the correct x and y coordinates, which are given. So how do we get there? Well, this offset can be calculated by the modulo operation in x and y, because we have performed the integer division of x divided by n, and that gave us the number of the indexing within for the bricks, and then we still have this remainder, which is the actual offset within the brick. So the x prime and y prime are the actual coordinates within our brick, and it is calculated from the original x and y coordinates modulo the n, which is the size of the brick. So the offset can be then calculated within the brick again in this way, which is again a linear layout of the memory within the brick. So now if we put it all together, then we can see that we are having the indexing of our calculation to get across the brick layout, the linear indexing of the bricks here multiplied by the size of the bricks, and then the plus with the coordinates which are within the bricks. So this will be the full index. This is already great, but there is a lot of calculation associated with it. So what can we do about it? Well, not much can be done about it, except of pre-computing some of this information. So let's have a look. This is what we sort of ended up with. This is the full indexing calculation. And let's put the actual values for these individual elements, which we have computed. So we can see the correspondence here, and we also see that we can separate some of these calculations to be, if we multiply, for example, with this n squared, we can see that we can separate this information into parts which can be maybe pre-computed, such as, for example, the nx divided by n, or, for example, the n squared, of course. But besides that, we can also separate it into two parts. One function which relates to values based on the x coordinate, and some function which can be separated which relates to the y coordinate. And these functions we can basically pre-compute for our x and y and store them in a table. And once we need to fetch this information, instead of calculating this information, we can just look it up. This will significantly speed up the computation of these indices, and the size of such a pre-computed table will not be too big. And that is all from the chapter 12 on data structures for graphics, where we have reviewed several aspects where data structures, efficient data structures, are important in order to not to explode the memory, or in order to perform a fast lookup or fast computation. We have started with various schemes and data structures for computing the neighborhoods or information within the triangle meshes. Then we were continuing on understanding how spatial organization of the scene can help us to accelerate computations, like, for example, ray tracing, or also rasterization with the BSP trees. And finally, we have been talking about how to store multidimensional arrays in a linear memory layout so that the cache coherency can be exploited. Thank you very much for your attention, and see you at the next lecture.